Okay, today I'm going to talk about motion in the plane. I'll also refer to this at times as 2D motion. So before we get into this, I want to just talk a little bit about vectors. Vectors is maybe something you've seen in past classes or perhaps physics. We technically were working with vectors in AB calculus. The thing was, because we were doing one-dimensional motion, so if you remember all our position, velocity, acceleration problems were like an object moving up or down, or perhaps, along the x-axis, right to left. So it was always sort of a positive direction and a negative direction. So when we were doing velocity and we gave a positive or negative, that was a vector quantity, but we didn't have to think of it really as a vector. And then the same is true for speed. Speed is the magnitude of velocity, essentially the length of that particular vector. But because our vectors were either always horizontal or vertical, it was always just the absolute value of that single value, okay? So one thing is that you're going to find, or hopefully you find, is there's a lot of connections as we do 2D motion to our AB motion problems. But it seems a little bit different, but if you think through it in the context of the fact that those were just trivial vectors, the ideas are all the same. We could apply everything we're doing today to 1D motion. It's just that one of our components would be 0 in both of those cases. Okay, so that changes things quite a bit, makes it a little bit simpler. But hopefully, with a little bit of an adjustment here, we can adapt to 2D motion. Okay, before I get into this, I'm going to talk a little bit about vectors. The reality is that to do these problems, we need sort of a rudimentary understanding of vectors. We don't have to get into all the operations of vectors that, it would be great if we had time to do that, adding vectors, multiplying vectors, things of that nature. We really just sort of need a simple understanding. So first of all, when we're talking about motion in the plane, sort of a common situation is I'm giving you a parametric equation. So two-dimensional motion is always going to be a parametric equation or functions to describe the motion in the plane. So we would have x is defined by a function of t, y is defined by a function of t. So if I graphed this in parametric mode and I see that actually gives me a path, the path of the object. This is not the same in one-dimensional motion because time was always on our graph. So for instance, vertical motion, if you remember, looked like a parabola, even though it goes up or down. Okay, so a little bit different here. So when I look at this gives me the path. What I don't see when I look at that curve is what the time is in any particular place. And what the time is, varies even if the path is the same. All right. So anyways, we have this x equals f of t, y equals g of t. I graph this, and this gives us the position of a particle as a function of time. Now, let's take one particular time, and we're going to leave this pretty abstract here. In the next problem, I'll tie this to an actual situation. If I wanted to know what the velocity is at that particular time, whatever time that gives me, I don't know, we could call it t equals a. What I would be interested in is the velocity vector, okay? So there's two components to a vector. That's direction, so where it's pointing, and magnitude. Okay, so let's say this is on the xy coordinate, and I have that this vector, this velocity vector, starts at 1, 1. So that's the position at t equals a, and then the velocity vector ends at 5, 3. Now, 5 comma 3. Now, the way we do these is we do what's called a component vector, and this isn't something you generally have to think of, but it doesn't matter where that thing's positioned. We can always position that vector so it starts at the origin. So whenever we see this type of notation, it's not a parenthesis, sort of a pointy edge here. It means that we're starting at 0, 0, and we're ending at that particular point. Okay. So in this case, it's actually quite easy to figure out. 5 minus 1, this would be 4, and 3 minus 1, that would be 2. So our component form of that vector would be 4 comma 2, and that's how we would describe the velocity. So the length of that vector would be essentially the speed, the magnitude, and then it points in that direction. It does not matter the fact that this starts at 1, 1 and this starts at 0, 0. They are the same vectors. It's direction and magnitude, okay? Now, so every time we calculate velocity, just remember it's in this component form. So even if we're finding the velocity of a curve and it's over here away from the origin, it doesn't matter, the vector is going to refer to where it is on the origin. All right, so let's get into it. For the most part, a lot of this is going to be intuitive for us. So if I give you this position function, x equals f of t and y equals g of t, velocity is just the x component, you take the derivative of it, y component, take the derivative of it. This also tells us direction, okay? So, you know, if this value is positive, it means I'm moving to the right. If this value is negative, it means I'm moving to the left, and they will ask you these questions. If the y component is positive, it means I'm moving up at that time. If the y component of this is negative, it means we're moving down. Acceleration, the rate of change of our velocity vector, that is just the double derivative of the original, okay? And then speed, if you remember in the past, speed was just simply the absolute value, and the reason why is one of our components was always 0, so this was kind of a trivial scenario. One of these was 0, but speed is actually the magnitude, the length of that. So speed is really just the distance formula. And as long as this is in component form, right, we're subtracting 0. So we're just going to take f prime of t squared plus g prime of t squared, and we take the square root. So for instance, the magnitude of this vector, whatever that time was, we don't really care, would be the square root of 4 squared plus 2 squared, so that would be the square root of 20. Don't bother simplifying or anything like that. So that would be the magnitude, which is the speed. Okay? And then total distance traveled, quite a bit different here. Total distance traveled, we are really just finding the length of the curve. So let's say I want the total distance traveled from t equals a to t equals b here. We actually want the length of the curve. Once again, when we talk about parametric equations, when we talk about 2D motion, this is the path of the object. So to find the total distance traveled, it's just the length of the curve from t equals a to t equals b, and we did that when we were doing the parametrics. Now, something to keep in mind, if hopefully this is why I say that this stuff isn't completely removed from 1D motion, because if you remember, we could do total distance traveled by taking the absolute value of velocity in there. Well, think about it, absolute value of velocity was the speed function, so we're still really integrating. Oop, I don't have the dt here, let's put the dt in there. So what we're still doing is integrating the speed function, right? That is the speed function, so we're still just integrating the speed function from a to b. Okay. So definitely want to get this all down in your notes, and then we'll start off doing some examples here. Okay, so here's our example. We are giving you a particle moves in the xy plane with position defined by x of t and y of t. Once again, this is a parametric situation. On the interval for t, so this is sort of the time here from 0 to 5. Notice no units are given here. When no units are given, we don't have to worry about them. And I will tell, in these types of problems, typically you're not going to see units like we saw sometimes with the motion problems in AP. So I went ahead and graphed what this parametric equation looks like on 0 to 5. Let's be clear, a lot of times we don't have this graph, and I will tell you, if you do need the graph, they give you the graph. There's really no time on the AP test where we're really graphing parametrically. It's just not something that we really need to do. This would be definitely a closed calculator scenario. There's no reason why you need a calculator here, so I'll do this closed calculator. Okay, so the first thing is we want to find the position at t equals 2. So since I'm given the position function, it's quite easy. I'm just taking 2 and plugging it into my, my parametric equation. So x of 2 is equal to 2 squared is 4 minus 2, so that's 2. And y of 2 is equal to 4 minus 1 is 3. Sorry, that took me a moment here. So what we're talking about, what we're going to be analyzing, at least for these couple, is what is this thing doing at that point, 2 comma 3. Once again, with parametric equations, time is sort of the hidden variable. The x and y are those locations here. Okay, so that's my position. Now we want to find the velocity. So in order to find the velocity here, what I need to do is I need to find the velocity in terms of t, since this is a closed calculator. I will tell you, if this was open calculator and I wanted to find the velocity, I would just use Math 8. Unless they specifically ask for the velocity in terms of t, then I would have to take the derivative. So my velocity in terms of t, once again, this is a component vector, would be 2t. That means it's going to start at 0 and end here. So this will be 2t minus 1, comma, and then 2. So my y component is actually always positive, always 2. So that means it's always moving in an upward direction. By the way, I did indicate its direction here, so that kind of gets confirmed by what we're seeing there. Okay, so, and you can see over here it's moving to the left. So until t equals 1/2, right, it's moving to the left because that velocity would be negative. All right, so that graph is confirming that. So we want to know what the velocity is at t equals 2, which is, just plug 2 into that. So 2 plugged into that is 4, that's 3. And then of course 2, doesn't matter what you plug into, it's a constant 2. So that's my my velocity vector. Strangely enough, was that? No. Okay. All right. So that's my velocity vector. So what that means at this point, if we reset this thing, the vector here, if we sort of move that to the origin, would start at 0, 0 and end at 3, 2. Instead, it starts at 2, 3. And ends, you could go up 3 over 2. Anyways, doesn't really matter here. We don't generally think about that. What is the speed at t equals 2? So the speed, the magnitude is, we're going to take the derivative, plug the value in, which is 3, square it. So this will be 3 squared plus, and then 2 squared. So it really is just distance formula, except, or you can think of Pythagorean theorem, however you want to think of it. So that's 9, so that's the square root of 14. No, square root of 13. And that is our magnitude. In other words, that is the length of that vector. So it shows you sort of how fast it's going. All right. So that is the first 3 things we're looking at. So the next things we're going to look at is we're going to look at the acceleration and then the total distance traveled. All right. Okay, so 2 more questions, and that will be it for example 1. So part D, what is the acceleration of the particle at t equals 2? So you'll notice I wrote down the velocity from the last problem, not that it would be that hard to figure out. So to get our acceleration vector, that's a dead. So to get our acceleration vector, okay, we're going to take the derivative of this. Now in this particular case, we get the acceleration of our x component is a positive 2, and the acceleration of our y component is 0. Now this is actually a constant acceleration, right? So it's a constant acceleration, so that means it doesn't matter what the time is, it's going to always be 2, 0. But in this case, let's go ahead and describe it. So normally at this point, if I want to find the acceleration, I plug it in, but this is always a constant 2, 0. Okay. That won't always be the case like it is, for instance, with like vertical motion. We know the acceleration is always a constant. Okay. All right. So let's move on to the next thing. What is the total distance traveled by the particle? I will tell you that typically when we do these closed calculator, usually we'll just do the setup. We won't actually calculate. And I say usually, there might be an example out there where they contrive the situation where you can figure out. But most of the time, this is going to give us an integral that is going to be difficult without a calculator. Now, if it's open calculator, not an issue. We just do the setup and then do Math 9. And once again, I would just do that in function mode. I wouldn't really worry about parametric mode at all as far as our graphing calculators. All right. So that means, and I'm just going to go do this over here. So it's going to be the integral. We're starting at 0. We're ending at 5. The square root of the derivative, or the x component, the derivative of the x component, squared, plus the derivative of the y component squared. And there you go. That is going to give us our total distance traveled. And once again, what we're really finding is the length of that curve from 0 to 5. Okay, So that is our first example. The next example I'm going to do is I'm going to change up what I'm giving you. So, and I will tell you that this is actually rare that they start you off with the position function itself. It does happen, but it is somewhat rare. All right, let's do another example. Okay, second example, and what I'm going to tell you, this second example is much more typical of something we'll see, for instance, on the AP test. So in this case, they're not giving us the position. They're saying this is the position function x of t, y of t, but they're not explicitly defining that for us, which, like I said, is pretty common. But they are giving us the velocity vector. So here is the x component. So realize this is also, you know, we can think of as dx over dt, and this is dy over dt. And sometimes they describe them that way, so don't be thrown off. Ooh, it's dy over dt. So don't be thrown off if instead of showing us specifically that it's a vector, they write dx over dt and dy over t. At time t equals 1, the particle is at 3, 5. So like what we've seen in past one-dimensional motion, when they give you the velocity, they typically will give you some sort of initial condition, which we're going to need, for instance, to find the position of the particle at t equals 2. Now this is open calculator, so we're not going to be deriving or integrating by hand. In fact, this would be exceedingly difficult to do that, or impossible for our in the scope of this class. So what I'm going to do is, first of all, I'm going to put this in my calculator. So and once again, function mode is where we want to be. So I would enter this as my y sub 1, and just keep in mind that when we need an x component, we'll refer to y sub 1, and the y component we'll put in y sub 2. Make sure you're in radians, of course. So now, if I want to do the position, I need to do these as two separate functions. We did this in the past with one-dimensional motion, but we just had one of these, right? So here we have to do both, and that's why we have two values. So we do not want to integrate this by hand, so we do want to do the setup. So to find what x of 2 is, x of 2 is equal to, well, we have our initial condition. We know that it's 3. It's at 3 at 2. So if I just integrated from 2 to 2, that would give me 0 and bring us back to 3. But we want this at the location that we want, or the time when we want to actually find the position, which will be, oh, I did that wrong, my bad. So this is the time 1 when we're at 3. So this should match here. And so if you get confused here, just think about this. If I plug 1 into the top, then 1 and 1 would give us 0, and that brings us back to 3. So that's sort of the check. And then this would be to the time that we actually want the position. And then this would be cosine of t squared dt. And that's going to give me my x position. Okay, my y position, for the y, I have the 5. Once again, that's also at t equals 1. So 5 plus, and then 1 to 2, and that's e to 0.5 dt. And from here, I plug this in my calculator like I normally would. So let's go ahead and calculate these things. So I've got 3 plus math 9. We're going from 1 to 2. And follow along if you want, or, you know, I think most of you know how to do this. I put this in as my y sub 1. Oops. And what I'm getting here is 2.5569, and I'm just truncating the 4 decimal places. And then let's do the other one. So start with the 5, math 9, 1 to 2, and once again I have this as my y sub 2. And there we go. We get 7.139, and that is 1. So my position at time t equals 2 is an x location of 2.5569, and y position is 7.1391. So if I looked on the graph of this thing, if I actually saw what the particle looked like, which I don't, that's what I would come up with. Okay. Now for this part B, hopefully I have enough room down here. For what value for a time 0 to 1 is the point on the curve at which the tangent to the curve has a slope of 2. So I want to know when the slope is 2. In other words, I want to know when dy over dx is equal to. Now realize that that actually is when this is my y, and remember, this is already the derivative. So we don't have to take the derivative, it's already in that form. So dy over dt over dx over dt. So this would be e to the 0.5t over, and then cosine of t squared. And once again, we're just calculating this on our calculator. So what I'm going to do is in my y sub 3 here, I'm going to just enter that as y sub 2, so vars, y bars function y sub 2, divided by vars, divided by vars, y bars function y1. And that's actually giving me my dy over dx function. Now I'm interested when that's equal to 2. So essentially, for y sub 3, I'm entering y sub 2 divided by y sub 1. That's going to give us this dy over dx term. And then y sub 4, I'm going to enter 2. Now, when I go to graph this, I'm going to toggle y sub 1 and y sub 2 off. So if you just move your cursor over the top of that, we can toggle both of those off. And now when I set up my window, realize that when I graph this, I want to just look on the x from 0 to 1. And then for the y, so this would be our x, we really only care about where it crosses 2. So for the y, I could do something like, I don't know, 1 to 3 would be perfectly fine. So let's go ahead and set that up. So 0 to 1, and once again, I'm in function mode, and I suggest you stay in function mode. So this would be 1 to 3. And taking a little bit of time here. All right, so second calc, intersect, first curve, second curve, and our guess, I don't know, 0.75. And what we get is t equals 0.8401. Okay, and that is our t. All right, so that's parts A and B. Let's move on to parts C and B. Okay, last two parts here. C, find the speed of the particle, t equals 2. So we actually already have our derivatives, right? That's dx over dt, that's dy over dt. So really all we have to do is put that in that formula, but it's t equals 2. So my speed at t equals 2 would be the square root of cosine of 2 squared, and then we're squaring that, plus, and then e to the 0.5, actually let's just call that 1 squared, and that will give us our speed. And once again, I can just use my calculator for this. Keep in mind, all we're doing is plugging 2 into we have this as y sub 1 and that's y sub 2. So, square root, vars, y bars function, y1, with 2 plugged into it, that's squared. Let's put parentheses in there just in case. Okay, plus vars, y bars function y2, plug 2 into there, squared, and there we go, 2.7957. That is our speed of our particle at t equals 2. And then finally find the total distance traveled from 0 to 1. Remember, this is just length of curve. And once again, you don't have to take derivatives because those are given to us. So 0 to 1, we're integrating cosine squared t squared. Okay, so we're squaring it, don't forget to square it, plus and then e to the 0.5t, and then squared, and then dt. So this we just enter in our calculator, and I would, once again, just advise you to use those vars, y bars, etc. So math 9, 0 to 1, square root, vars, y bars, function y1, squaring that, plus vars, y bars, function y2, square that, and there you go. 1.5946, and that would be the length of the curve from 0 to 1, which is also the total distance traveled by the object. Okay,